All right. Our first speaker is Joel Gruse, and he comes to us as Vice President of Data Science and Engineering. He has 2 master's degrees. I'd love to have a master's degree in social science. I think that's so cool. Also in math. And my word for him is cowboy, because if you look at his LinkedIn profile, he's got like this cool hat on. So I suspect that he likes to wrangle data with a lasso. Welcome, Joel.
All right, thank you. Are my slides up? Yes. So I'm Joel, and I'm going to talk to you today about simplicity. Can you start my timer? Thank you. I work at Goldman Sachs in our consumer business, trying to figure out ways to use machine learning and NLP to make our customers' lives better. Before that, I've had a long and varied career in data science, software engineering, writing books, data analysis, and so on and so forth. And recently I moved to Texas, which is why I wear the hat, but also I do like to wrangle data. So this is maybe the 4th or 5th time I've spoken at this conference, and every year the same thing happens. Khalifa emails me like 4 months in advance and says, what are you going to talk about? And I say, I don't know, and he says, give me a title. And so I give him a title, and then later I have to figure out like what that actually means. So this year it was different because Mark emailed me, but still I was thinking a lot about simplicity. So I said, okay, I will, my timer's frozen. I will talk about simplicity, and then I had the last 4 months to figure out what I wanted to say, and I think I got it down. So most of you have never worked with me, but if you did, you know that when you're starting a data science or machine learning problem, usually what I'll say is, what's the simplest thing that might possibly work? And sometimes I forget to tell people that, and so then I have to say, what's the simplest thing that might possibly work, and why didn't you try that first? And eventually people would learn to try simple things first. But what makes something simple? What makes a machine learning model simple? What makes a data science practice simple? How do I even know what's simplest when I'm trying to decide what to do first? So I've been thinking a lot about what do we mean when we talk about simplicity in machine learning and data science. So last month I saw this tweet about the cult of complexity in the machine learning community. Big equations, big words, big models. So maybe simplicity is the opposite of these, small equations, small words, small models. Doesn't feel quite right. Here's a similar idea. Simplicity is a great virtue, but complexity sells better. Simplicity requires education to appreciate. Okay, so this is my attempt to appreciate simplicity. So here's another tweet I found. Simple solutions are easier to implement and scale than complex solutions. We need to start acknowledging the power of simple. So in order to acknowledge it, like I keep saying, we need to figure out what does it mean for something to be simple. So this is a data science conference, so I thought I would maybe ask DALL-E to explain simplicity. There's a lot of talk about how maybe prompt engineer is the job of the future, figuring out how to tell these models what to draw. I hope it's not the job of the future because it turns out I'm really bad at it. I cannot get the machine learning model to draw anything good looking. This was my attempt to get it to draw a comic that explains simplicity. And you can see that none of the comics actually explain simplicity. I also asked it for a realistic photo. That didn't do any better, so that's not helpful. I asked it for some pixel arts. These didn't explain a thing to me. I tried an MC Escher drawing. These are cool looking, but they also don't help. And finally, I tried a cartoon. And these look like New Yorker cartoons, but they don't, again, do much to explain to me what does it mean for something to be simple. So, I started thinking maybe simplicity is the opposite of complexity. So let's think about it like that way. Complexity is something that we're used to thinking about in terms of machine learning. You often see graphs like this where as a model gets more complex, it's more likely to overfit and the variance goes up and things like that. So maybe that means as simplicity increases, we're more likely to underfit our data. But that doesn't really feel right to me either. I mean, here we're using complexity as kind of a synonym for model capacity. And I don't think that's really how I want to think about simplicity. And you can find people giving examples of here's a bunch of simple models that outperform sophisticated models. So simple is something that's not sophisticated. It's interesting, but it's also kind of not how I want to think about this. So instead, I'm going to really deeply seek simplicity, and then you should distrust whatever conclusions I come to. Okay, so why was I spending a lot of time thinking about this, 4 months ago? The last, let's say, 5-6 years, I've been doing a lot of natural language processing. And so I'm always talking to people about NLP problems. And I talk to a lot of people about text classification. And so if you're not an NLP person like me, text classification is pretty much what it sounds like. You have an email and you want to classify it. Is this spam or not? Or you have a piece of text, a tweet, and you say, is this a positive sentiment or a negative sentiment or no sentiment at all? Or you have a blog comment and you want to decide, is this comment toxic or not? Or here's a talk about simplicity, and is it worth attending based on its abstract or not? Or here's a description of the machine learning model, tell me if it's simple or not. So there are a lot of ways that you could approach this text classification problem. So one of the very classic ways is what's called naive Bayes. So going back to this idea of spam classification, you chop the spam into words, you take some training data set, you count up how often does each word appear in spam emails, how often does each word appear in not spam emails, you use Bayes' theorem, and it sort of falls out. It's a simple model in the sense that it doesn't have that many parameters, sort of a couple per word, and this is a very classical approach to spam classification. A lot of the first models were like this. There's a chapter in my book about this. You could probably implement it yourself from scratch in an afternoon if you set your mind to it. Another simple approach is the logistic regression model. So somehow I take my email and turn it into a vector of features. That could be word counts, that could be TF-IDF, doesn't really matter. And then you learn some weights, one per feature, and then that's basically like one parameter per word of vocabulary. And again, that's a relatively simple thing to do. And then, about 6 years ago, the state-of-the-art thing to do would be to use some kind of recurrent neural network. Take your email, chop it into tokens, convert it into a sequence of embeddings, feed it into one of these LSTM models, and classify the hidden state. So now you've got many thousands of parameters, and there's a lot more going on here. So this is more complex, and there's an asterisk by thousands of parameters, and I'll talk about that in a second. And these days it's the year 2022, so you might want to use a BERT model. You take your email, convert it to a bunch of word piece embeddings, segment embeddings, position embeddings, feed it into a transformer model, use the final output as input to classifier, fine tune it. And so now, if you use BERT base, you've got like 110 million parameters. So that's a much bigger, much more complex model. And so my question, maybe it's more of a poll because I don't actually know the answer. Which of these is simplest? Any, shout it out, I don't, any ideas? No?
Who wants to say number one?
I really don't. I don't want you to say anything. I'm really curious. I don't have a right answer in mind because I don't know how I would answer it. Okay, so that's one vote for Bert. One vote that I want you to say number one, but I don't particularly want you to say anything. Two, okay. Four, good. Diversity of thought, I like that. But now the question is, which one would you recommend? You have a friend who's a data scientist and needs to put a model into production and classify it spam or not spam. And what are you going to tell your friend to use? You're going to tell them to use BERT. And this one I actually do know the answer to because I do this all the time. I talk to people and they're saying, I'm going to use naive Bayes to solve my problem. Or I'm going to use, I'm going to use TF-IDF vectors and then feed them into XG, all sorts of, you wouldn't believe the things I hear. And then I tell them, why did you not just use BERT or distill BERT or REBERT or whatever? And so I feel like I've spent a lot of the past few years just shaking people. Why are you not using BERT to solve your problem? It would solve your problem. But I'm also telling people, try the simplest thing first. And so I spent a lot of time grappling with this notion that BERT is not the simplest thing you could possibly try. There's a lot of simpler things to try, but I'm telling people, don't try those other things. You're wasting your time. And so that's where I really got into this kind of struggle. And you know, when I took a step back and thought about it, when I showed you that LSTM model, I put an asterisk by it having thousands of parameters. And that's because I sort of slid in there, embed your model, embed your sentence as a glove vector or some other kind of word-to-vec vector. And if you download the glove vectors, that's like hundreds of megabytes of data. So you secretly have, you know, these millions of parameters that are hidden in the glove model that we're sort of not counting because they've been taken away from us and we're just using that model as is. So does the complexity of glove vectors count for the complexity of the LSTM model, or do we think about just the LSTM model itself? So I don't know, but that was sort of the next point I struggled with. And so let's get back to this BERT model. You know, I have all these pieces here, but you could also think of BERT as kind of a black box where I put a sentence into it, and it returns to me an embedding of that sentence, right? So, you know, BERT is something that I put in text, it hands me back an embedding, and then I train like a small classifier model on that embedding. And if I think about it that way, the same way I was thinking about, you know, the glove LSTM model, suddenly we've got thousands of parameters, not millions of parameters. Now, this is cheating because when you fine-tune BERT, you generally adjust the, you know, millions of parameters a little bit too, but even if you didn't, conceptually, you're kind of doing the same thing. There's also hidden complexity in, you know, the first couple of models. When I say convert text into a vector, well, there's a lot of ways to do that, right? Should I filter out stop words? Which stop words? Should I do stemming? Which stemming? And so on and so forth. So it's not just take text, get a vector. It's you have to make a lot of modeling choices that make the process suddenly not as simple as it might seem at first. Whereas with BERT, you just sort of shove the text in and get a vector out. And you get those sorts of things for free. So, you know, this is a lot of clutter. How do we get simplicity out of it? So I'm going to talk about woodworking for a minute. I hope it might make sense. So I have a plan that I'm really going to get into woodworking. It's sort of on my to-do list right after I write this talk is like buy some woodworking equipment and start doing woodworking. But in the meantime, I watch a lot of woodworking videos on YouTube. Like a lot. And so I'm probably in like the top 1% of people in terms of how much I know about woodworking if you restrict it to people who've never done woodworking. So I'm a savant with watching woodworking YouTube videos. Like I can tell you a lot of things. I've just never done them, and I don't know if I could do them. And so, you know, imagine that you and your friends are trying to like build a kitchen table, and you're not doing a good job of it because, you know, one, you're the outputs of like DALI, and two, you don't really know much about woodworking or what you're doing. And you decide, we don't want these like big, chunky legs. We want it to have like beautiful, you know, tapered legs that glide down to a point and are nice looking and maybe less sharp if you bump into them. And so, you know, one thing you do is you go to Amazon and they'll sell you tapered legs. $175 is not cheap, and you don't get the kind of satisfaction of doing it yourself, and your YouTube channel won't get many subscribers if you just buy stuff off Amazon instead of woodworking it yourself. So how do we make these? Well, you know, if you're an expert craftsman, you take a piece of wood, you put it in a vise, you mark off things very carefully, you take your handsaw, you measure it, you saw, it's a lot of work. It's very involved, it's very complex, and there's a lot of ways it can go wrong. But what you discover if you keep watching these videos is that, like, yes, that's how the real artisans approach it, but there's another way to approach it, and that's using this idea of jigs. And so what is a jig? A jig is basically a little device that you build yourself that has a lot of the complexity baked into it. So this is what's called a tapering jig if you need to cut something at an angle, like a leg, for a table. And so what you do is when you're setting up the jig, you measure very carefully, this is the exact angle I need, this is a stop where I want the thing to go, and then you slide your piece of wood in. It's almost foolproof, like it has things it butts up against and it can't go anywhere, and then you run it through the table saw. That's almost foolproof insofar as using a table saw, which it isn't, be careful of your fingers, but basically most of the complexity is hidden in this jig, And what's left for you to do once you have this jig is very simple, relatively simple. And so this sort of reinforces this idea to me that how simple something is not just how complex all the parts are, but also like how difficult are the parts that I actually have to do myself, and what is the bar to trying it. So if you wanted to train a BERT model in like late 2018, you were signing up for a lot of work. There was a library called PyTorch pre-trained BERT, which eventually became Hugging Face, and this is one of the examples from its original repo. And this is an example of how to train a text classification model. You can see that we're in line like 530 and it's still going. And so if you wanted to do this on your own data in late 2018, it's not that you couldn't, but there was a lot to do and a lot that could go wrong. And it was really complex. Now in 2022, doing the exact same thing, but now using the Transformers library, is about, you can see 20-ish lines of code. And I hid some things, but still, this is about 20 lines of code to train a model. And there's a lot fewer ways that can go wrong because a lot of that complexity has been taken away and put into the library where it's hard for you to mess it up. So BERT is not a simple model. Like, some of you voted for BERT being like the simplest model. I don't think it's a simple model. It's not a simple model. It's actually quite complex what it's doing, but these days it's relatively simple to use BERT and to use it correctly. And it's relatively simple to get good results with BERT. In fact, it's simpler to do that than with one of the simpler models, I would say. Another quick example is sorting. Some sorting algorithms are really simple. They expect you to memorize them and regurgitate them at a job interview. When I interviewed at Google, I memorized like every sorting algorithm and never use them and wasted brain space, whatever. But who knows what sorting algorithm Python uses? Anyone? TimSort. Who knows how to implement TimSort? No one. Just TimSort is like super complicated. It's this weird hybrid insertion sort, merge sort, whatever, that you would never in a million years come up with yourself. But the thing is, no matter how complicated it is behind the scenes, Python has insulated you from that by giving you this sort API, and it just works for you. And even Python beginners use it without any problems. Well, they have problems, but not problems on account of it being a complicated algorithm. They have problems for other reasons. And so the place that I got to was that as our tools get better, the boundary between simple and complex changes. And I think this was the important point to me. So returning to this idea of simple solutions being easier to implement and scale, how easy a solution is and how simple it is depends a lot on the tools and abstractions you have for working with it. With a tapering jig, it's simple to implement and scale making tapered legs. Without one, not so much. With Transformers library, it's pretty simple to train a BERT classifier. Without it or some equivalent, it's really complex. With the Python standard library, it's simple to use a stable hybrid merge insertion sort. But in other languages, it's not. And so I saw this tweet the other day, and this sort of reinforced this idea I was getting at. This is the CEO of AngelList. And he said, I'm often asked, why use AngelList to run a fund? My answer, AngelList abstracts away all the complexity associated with starting and running a fund. And so I thought this was a really interesting notion, abstracting away the complexity, right? The complexity is there. Like to start a fund, you have to fill out some paperwork, you have to get the lawyers to do this, you have to fill out this form and that form or whatever, but they're abstracting that away from you. They give you an API that makes it simple by abstracting the complexity away. And so sometimes things can be simple, not by lacking complexity, but because complexity has been abstracted away. And so, I sort of take this as my launching off point. As you're doing data science or machine learning or whatever, think about how can I abstract away this complexity and leave myself with something much simpler to work with. So that could be, pre-trained. Obviously, in NLP and vision and other areas, these pre-trained models allow us really not to worry about some of the more complex parts. These are libraries that are easy to use. I used Hugging Face as an example. There's plenty of others. project templates so that when I start a project, I don't have to worry about, oh gosh, where am I going to put my data, where am I going to put my outputs, where am I going to put my model. I'm just going to do it this way and not worry about it. It's about building clean APIs. It's about implementing best practices across your team. And it's about sharing processes so that there's fewer things that people have to worry about and that can go wrong. So, I will wrap up with this quote from Lao Tzu about abstracting complexity away. Okay, it's not actually about that, but it's sort of about that. Okay, so manifest plainness. I think this is a message to some of you who have too many stickers on your laptops that maybe you should have fewer. Reducing selfishness, which I choose to interpret as being about like share the GPUs with other people and don't hug them all for yourself. Have few desires. I don't get this one. Can't make much sense of it at all, to be honest. And then embrace simplicity. So if there's a moral to this talk, it's maybe that simplicity isn't simple. Things that seem simple sometimes are not. Things that might seem complex could be a simpler choice, and that simplicity is really about not just the concept we use, but the tools we use and the abstractions we use and the processes we use. So thank you.